So I kind of scared you, maybe. I told you in the last video, oh, we've got an equation that you probably learned in 151 and 152, and this equation can be used in the IC field because very often we might have to make this type of mobile phase. So I told you that NaOH can be used as a mobile phase. KOH can be used as a mobile phase, and the combination of bicarbonate and carbonate can be used as a mobile phase. And these are kind of the most common mobile phases that are out there. Well, that's kind of the key word. I'm going to put common here. Okay. So there's tons of other choices that we can use in ion chromatography in order to do our separation. We've got recipes after recipe after recipe, really depending on what we want to separate. Are we separating anions? Are we separating cations? Are we separating things that all have the same charge? Or are we separating things that have different charges? Are we separating things in very high amounts? Are we separating things in very low amounts? So those are just the most common scenarios that you might run across in a lab. However, there's some others, and some of these other choices that you might see, one of those categories is something called a buffer. And we're going to have to go back and kind of review what a buffer means, because it could have been a while since you've seen the definition of buffer. So a buffer is basically a combination of a weak acid and a weak base. And that combo is put together and it helps control the pH of a solution. Well, we're already seeing charges are playing a role, right? And in a previous video, I told you that in one case we can use acetic acid. But acetic acid is a weak acid. And it gives off proton, but it doesn't give off all the protons, right? Okay, well, this is a weak acid choice, and the complementary weak base choice would be, well, what would this be after it gives off the proton? Well, that's CH3COO minus. And that will typically can be ordered and come to us in form of a salt. And we can use acetic acid and sodium acetate as a combination for making a buffer. And this will help control pH, which helps control charges, which is really how the IC system works. So sometimes I'm going to be reading a method or an SOP, and it's going to say prepare a buffer that consists of the following. And it gives me numbers to weigh out, and I'll measure those amounts out in gram or milligram. Tells me what to dilute it up to, and this is going to be a proper buffer that will control a pH environment. Well, the acetic acid and acetate is just one of those examples. And there's tons of examples of a buffer that is out there. But let's say that I'm required, because I'm a lab technician or an entry-level chemist or a laboratory worker, right? So let's say that I'm required to make my own buffer, and I'm going to have to come up with my own recipe. I mean, I should be able to know how to do this kind of thing, right? So if I'm required to make my own buffer, what I have to understand is that there's an equation that's out there. And that buffer is probably made to get you around a certain pH level. And as long as we stay at that certain pH level, then we have control of whether or not these ions are really ions. I've got control of their charges. So let's say I want to make a buffer that has a certain pH. So pH is equal to, and what we need is the pKa of the acid plus log of the concentration of the base divided by the concentration of the acid. We kind of saw this in the solutions chemistry class. We talked about how to make solutions, how to prepare them, and buffers were one of these. And we used these types of equations during that time. And we call this the HH equation. And the HH equation stands for Henderson-Hasselbalch. That's BALCH. Henderson-Hasselbalch equation. All right. So this equation, the HH equation, would have to be used in a lab environment. This equation will tell us how much of the base and how much of the acid to weigh out in order for us to get the pH that we are after. There's a couple of ways that we can target this equation. One way is going to be a little bit easier than the other way, and we're going to start off with the easy type of problem first. So the question is going to say, well, what is the pH of the solution of a buffer that I'm going to be making if you took 0.75 molarity acetic acid and 0.50 molarity sodium acetate, and the pKa is 4.74. So this type of equation is saying this is how much acid you've used, this is how much base you've used, and we've done the easy work, and we've went ahead and calculated the concentration for you. And here's the pKa for acetic acid, because that's the acid that's involved in the buffer. What's the pH? So pH is equal to pKa plus the log of the base divided by the acid. These numbers for base and for acid, those require molarity. Okay, you can't put grams in there. You can't put ppms. You can't put anything in there at all other than molarity. It has to be calculated in molarity strength. All right, so what I'm going to do to solve this problem, the pH of this buffer that I made, maybe for the IC instrument, is going to be the pKa of acetic acid, and that comes from a table, or it's given, 4.74, plus the log of the concentrations of the base in molarity, and that is given to me, 0.50, divided by the concentration of the acid in molarity, and that's 0.75. All right, so I'm going to bring up the calculator here, so that way you can kind of follow through and see what I'm doing. We're going to minimize this down. You don't need that big of a calculator. All right. So now I'm going to take 0.5 and I'm going to divide that by 0.75, and I'm going to get 0.66666666666. All right. So now I need to log that number. So I'm going to log that number, and I'm going to get this negative 0.176 as the answer. You can kind of see up here at the very top, log of 0.66666 all the way across, and that answer is negative 0.176. So I'm going to kind of do baby steps here. 4.74 plus this negative, and remember what we said, 0.176 is the answer. And now I just need to simplify this out, and I need to take 4.74, and I need to add a negative number, or just basically subtract the number, 0.176. And that gives me a 4.56 as an answer. All right, so that's an easy type of Henderson-Hasselbalch equation buffer problem. All of the things that you need basically laid out for you already. The concentration in molarity of your acid, the concentration in molarity of your base, and the pKa is all given, and it basically says what is the pH of the solution. Now, there's a couple of different variations of the problems that you might see. And we're not going to work through all of them, but I'm going to kind of give you those scenarios. The first type of alternate scenario that you might see is that they're going to give you grams or milligrams of the acid and of the base that was used. What you're going to have to do from this point is you're going to have to calculate the molarity of each one of these, and then those two molarities can be lumped together into the HH equation. To go from gram to molarity, you need to understand that gram needs to go to mole, and you use the formula weight for that. And then when you get mole, you're going to divide by the liter that you're making. How much buffer are you making in total? And that will give you the molarity number. This type of calculation I'm not going to go through because, quite honestly, you should already know how to do this at this point. So gram to mole using formula weight. And then when you get the mole, you need to divide by the liter, total liter that you're making, to get molarity. That molarity will have to be calculated for the acid and base, and then that can be plugged in to the HH equation after that. And then they can give you the pKa of that acid that you're using, or you can find it. And then you will solve for the pH that you have just made. What should the pH be if you have prepared it the proper way? And that can be checked with a pH meter. The other scenario that you might see, it will say you are required to make a pH of, let's say, 6. And you are going to use this particular acid. And they give you the name of it. Which also means that you can find the pKa of that acid as well. So you'll know that. So let's say that your pH is equal to 6 and your pKa is 5.21 plus the log, and you will have to solve for A and HA. This is a different type of equation because the numbers that you're solving for here is the molarity of A and the molarity of HA. You'll have to subtract the pKa's from each side. You'll have to inverse log that number. That will give you A and HA, which are two variables, and those two variables will have to be simplified into terms of each other. They will have to give you a total that you're after, so one of these will kind of be X, and one of these will be your total minus X. That's traditionally how these problems are handled. So you will have two variables, one on the top, one on the bottom. You'll have to use a little bit of algebra in order to solve that problem. And again, I'm not going to go through an example here because we did this in the Solution Chem course, and you should be able to calculate this HH equation. If not, you can find examples on the internet without a problem, but there's your example of the HH and preparation of a buffer. Okay. Something else that I want to talk about with mobile phases. Very often you're going to hear us that you will have to equilibrate the instrument. And when you equilibrate the instrument, that means you're going to allow the mobile phase to flow through the entire instrument and out the other end. This equilibration time takes about 30 minutes, and you have to do it daily. The only time that you do not do it, though, is if you leave it running overnight. If you leave it running overnight and you've not stopped the mobile phase from flowing through the machine, then you do not have to wait on an equilibration because mobile phase is already going through it. It had been going through it all night long. You've come in the next morning, you filled up the mobile phase jugs, and you just allow it to keep pumping. So you don't really have to equilibrate it every day if you're running it 24/7. It's always a good idea to hit the reset button, though. After so many number of days or so many number of hours, it's always good to kind of just stop it, kind of give it a good cleaning, make sure it is equilibrated the proper way before you go on and start running more and more and more samples. So it's just a way that we can saturate the entire instrument with mobile phase. It makes sure that our baseline can flatline, and it makes sure that things are ready to be holding your sample when you begin to inject it. So again, if you run it overnight, no big deal. Just kind of pick up from where you left off and you'll be okay. The other thing that I want to say is this concept of filtering the mobile phase. Some people are real particular with this, and some people are not. Quite honestly, we don't really filter our mobile phases on the IC instrument. We probably should, but we're not using nasty things and nasty mobile phases, and for us, we typically make them fresh, and they dissolve very well. There's very small amounts of things, and we just don't really filter them. But it's a very good idea to do it. We just don't take that step. We're kind of lazy when it comes to that. The filtering aspect of the mobile phases, you want to send through a 0.45 membrane filter. These membrane filters you've probably have used before. These are the typical small syringe filters that go onto the end of those syringes, and you can push your sample through them, and you've probably have prepped samples, small amounts of samples before in that way. The problem is that filtering the mobile phase, that's 2 liters of stuff. No one in their right mind is going to sit there and filter 2 liters of mobile phase through one of those little small syringes with a little small syringe filter on the end. So there's other options that are out there for us, and I'll show you what these options are in just a second. But 0.45 micron filters are typically the most common. Keep in mind that these can go smaller. So I can go to 0.2s and stuff if I want to. It just really depends on how particular I want to be. But 0.45 is typically the go-to number almost every time. Good things about filtering is that it will prolong your column. So it leaves it alive for a little bit longer, and I can get more use out of that column because it's not been damaged at all. And it also protects the pump. The pump is basically sucking your mobile phase through. And if your mobile phase starts to get a little slimy or contaminated, that gunk is going to go into the pump, and that pump will then become destroyed. And you'll have to take it apart, you'll have to clean it, you'll have to put it back on, all kinds of crazy stuff that you're going to have to do to the pump in order to get it to work again. A couple of things I want to say about the membrane filters. When you begin to look at the 0.45 microns, okay, and you go into the membrane filter world, there's going to be tons of choices that you can choose from. These choices are basically material that the filters are made of that you are using in a laboratory. What you want to do here is say no to cellulose. All right, so say no to cellulose. Cellulose actually has a tendency to release ions, and they're not very stable at high pH levels. Because of that, this is going to contaminate your mobile phase for you, and if you want to stay super clean and you want your baseline minimized, then cellulose could be a problem. So if you've made this mobile phase and you're pouring it through the micron filter, and you have chosen a cellulose-based micron filter, then you are doing more damage than you are good, because now all of these ions, there's a possibility that it will start to break down at very high pH levels, will start to go into your mobile phase and gunk up your system, and your conductivity could go through the roof. So say no to cellulose and you'll be okay. There is a term that we look for. These terms, most of the material that are out here are actually hydrophobic. Hydrophobic basically means afraid of water. So we are working in a water environment. We are making a water-based mobile phase. And if we take our mobile phase and we send it through one of these choices, those choices are hydrophobic, it will basically not filter for us. We're going to have a very hard time to send it through. So because of that, companies know this. They know that you don't want to use cellulose. And they know that these other choices are a little more plausible, but they know that these things tend to be hydrophobic. What they do is that they change the characteristic of it, all right? And this characteristic, when you order these membrane filters, you will see this word hydrophilicized or philicicide on the front. This is typically PVDF or PTFE. PVDF is going to stand for polyvinyl pyridine difluoride, and the PTFE is polytetrafluoroethylene. That's what those abbreviations stand for. They are very common materials in membrane filters. So PVDF or PTFE, those are the ones that you would probably want to gravitate toward. They're typically the cheapest. If they're modified and hydrophilic, then they will take your aqueous mobile phases, and that requires a little bit of modification on the company's part. So just make sure you see that word hydrophilic on the container, and you will be perfectly fine when it concerns filtering these mobile phases through the system. So this is what you're going to see with the filters when you get to this point, if you get to do this in a lab one day. They are not the little tiny membrane filters that you're seeing that we've always used in small sample prep, but this is more of a membrane filter. So what you're seeing here is a multiple part cup that you will have to put together. And there's two versions here on the screen for you to look at. The one over here to the left, this is more of a disposable, ready-to-go filter. So here you see a cup at the top, and this cup down here at the junction where this yellow piece starts, that is the area that has your membrane filter right there. And then you can have an aspirator hook up to the side, and you can pour your mobile phase through these, and your mobile phase will go through the filter and down here at the bottom, and then this will be your filtered mobile phase that you can unscrew this cap, pop it off, and take your filtered mobile phase at this point and pour it into your jug. Get ready for the IC instrument. So these are more disposable. They're more one-time use. The filter's pretty much ready to go in them. And it just really depends on the company that you work for if they want to go this route or not. If they don't go this route, then they will have a multi-use filter that you will have to replace the membrane filter on your own. So up here at the top, this is basically the cup, and that cup is going to be represented here to the left. And then you'll have a clamp, and the clamp's purpose is to keep the top part of the filter and the bottom part of the filter together. So that's kind of the yellow piece here, but now this is going to be a metal clamp that seals these two pieces together. So the yellow piece that you're seeing here that attaches to the receiving vessel down below, that's here with the nozzle and the aspirator on it. And as you can see, there's this removable piece in between the two. So the top sits down onto the bottom, and this clamp holds those two pieces together. And in the middle, you'll have this wire grid or mesh. And this wire mesh will be the support that you will need to put your plasticky membrane filter on it, because it kind of does look like a piece of flexible plastic in a way. It'll feel very smooth. It will be very flexible. So this wire mesh grid will be the support. You'll put your membrane filter on top of that, and then the top sits down on it, the bottom sits up underneath it, and this clamp will hold all of those pieces together. And you'll take that contraption and you will plop it down onto a Erlenmeyer flask or a vacuum flask, and then you will filter the mobile phase through just like you did over here to the left. So this is multiple use, over and over and over, but you will have to change out the membrane filters that are right here in the middle of this whole contraption. The membrane filters will come in boxes that look like this. Here you see hydrophilic version of PTFE, and it looks like the pore size that they chose in here was 0.22, not 0.45. Again, that's okay. It just really depends on the company and what the purpose of it is. Maybe they want to be a little bit cleaner, and the 0.22 will allow them to do that. What do these filters look like on the inside of these cases? Well, they look kind of like this. Up here at the top, this is what you have traditionally seen in our program probably up to this point. These are one-time use filters. They're already packaged together into a little casing, and you plop them onto an end of a syringe, and these are meant really for a very small amount of substance. The larger membrane filters, they're right here. And these membrane filters are the pieces that will go onto this wire grid, or that are sitting between this top compartment and this bottom compartment here. It's those membrane filters that we're talking about. As you can see, most of them are white, just like they are in the syringe filters when you've used them. They're very flexible. They're very plasticky feeling. And a lot of people get surprised when they hold one of them in their hand for the very first time. Here's a case of different ones. Most of the time, these things are separated by pieces of paper, and they will actually try to use the paper as the filter. I've seen that happen before because you're so used and trained yourself into talking about filter paper that the protective top and bottom layer that's there to separate the membrane filters from each other, people believe that that is the filter that they should be using, and it is not. So you just got to be careful with that. This is more plasticky filling. It is not paper filling, and the paper pieces are only there to separate the filters from each other. Here's another picture of a membrane filter. These are kind of super clean. They're packaged individually instead of in cases or in boxes. And you would actually take one of these out and you would peel the backing off of them. And there's going to be a piece of paper on the top still and a piece of paper on the bottom most of the time. And you will throw those little pieces of paper away and you will use that whitish, plasticky, flexible membrane filter in the middle. If you zoomed in and took a look at these membrane filters, this is what you would traditionally see. The different materials give to different pore sizes, which gives to different flow rates. So here you're seeing the nylon that's magnified versus the PES that's magnified. And nylon and PES are different membranes that you can choose from in addition to the ones that we've mentioned already. We've mentioned a total of 3. So this is kind of what we're after, and this is why there's so many choices. It really just depends on what you want to filter, what kind of pore size are you after, and what kind of material are you filtering at the same time. And we'll talk more about that in just a second, or in the next video. And then here's kind of the whole contraption setup as a whole. So what you're seeing here is the vacuum filter that's been clamped together. So I've put my membrane filter inside of there on my own. I'm going to pour my mobile phase through that filter. It's going to go through the membrane filter and down into the bottom collection flask. And that way I can then transfer that into a mobile phase jug and do what I need to do with it. This aspirator has to be hooked up to some kind of pump, and what you're seeing here is an external pump. And these can be happening in the lab. You don't need a sink basin in order to create a vacuum aspirator. The sink will allow some suction to come through, and it's a very convenient way for us to do it. But if we had a standalone pump, then that would allow us to do that as well. So that's what you're seeing right here. So this pump is creating the suction that's needed to pull this mobile phase through so that this process can happen much quicker. So in the next video, we'll talk about these membrane materials. You know, there's a reason that we would use some of them, and I want to go over through some of those choices and tell you why you would use maybe nylon over some of the others, why you would use PES over some of the others, and we've kind of already talked about why we shouldn't be using cellulose at all, period, for this type of process. So that's going to happen in the next video, so stay tuned and come back and we'll have another chat.